Okay, now we're going to take a look at a special class of problems called static problems. Static meaning, of course, that nothing's moving. Nothing has any velocity, nothing has any acceleration. It's all just sitting there still. Let's take a look at this problem. Supposing we have two hanging masses tied together by a little knot, and then a third hanging mass, which is unknown, draped over a pulley. This little stuffed teddy bear is hanging there. And our goal is to find the mass of the stuffed teddy bear. So how do we attack such a problem? Well, you want to examine the setup and look for a place where all the forces meet. And in this problem, it's clear that all the forces meet right here at the knot. What kind of forces are present? Well, there's tension forces for sure. 3 tension forces. So let's draw them in there. There's a tension force pulling up in this direction. There's a tension force pulling down over this way to the left, and then there's also one going straight down. There's also technically a small gravity force on that knot because it does have some mass. But that gravity force is so very small that it can be ignored in comparison to these 3 very large tension forces. So how big are those tension forces? Let's see if we can get some, let's see if we can figure out exactly how big each one of these are. And get some numbers on those forces, or at least some symbols. Let's look at this one to begin with. If we trace this force back, this tension is the same everywhere in the string, including on this side. So this tension is the same as that tension. But this tension must be exactly equal to this gravity force, because this is not moving. It's static. So the gravity force down equals the tension force. We can trace that all the way back. And so this tension force here we can properly label as, if this is M1 over here, this must be the exact same as the gravity force. We'll just call that M1 times G. And by a similar argument, if we trace this tension force straight down, we can see that this one here must equal M2 times G, because that tension force has to be just as big as the gravity force. And then our third tension force, if we trace it back to the bear, must be exactly the same as this gravity force. So that's just regular M, no subscript on that guy, G. So there are our 3 forces, and like I said, we're ignoring the gravity force because it's small. And so the question is, how do we set up a positive direction for all this? Normally, you set up a positive direction so that it's in the direction of acceleration. But since there is no acceleration here, we are free to choose any direction we wish as positive. Let's just go back to the old standard Cartesian coordinate system. We will choose the x-axis. We're going running right through the knot like this, so that'll be our x-axis. Our y-axis will run up and down. And then anything to the right will be positive for x, and anything up will be positive for y. Okay. To attack this problem, though, we really want to begin with Newton's second law, and we have to think of Newton's second law in both directions, x and y. We might not use both directions, but certainly both should be available to us. So we're going to separate our thinking, x and y, and we're going to write Newton's second law for each. So we can write Newton's second law in both directions. But since nothing's moving, the one thing that they both will have in common, both x and y, is that the acceleration is 0. So this right side of the equation here will be a 0, as will the right side of the equation over here. So let's begin by looking at the x side. Let's look at all the forces that are running in the x direction. If we examine this force, you can see that it's purely in the y direction, straight up and down, neither pointing to the right nor to the left. So this m2g will not figure at all in our equation over here. The other two forces, however, will. m1g is pointing somewhat to the left and somewhat up. mg is pointing somewhat to the right and somewhat up. Let's see if we can break this force up into an x and y component. So I'll choose some color, maybe like blue, for the x component, and we can draw this here as the x part of that force, and we'll draw this guy here as the x part of that force. And while we're at it, maybe we'll pick a color like maybe green. I'm running out of colors. Will be good for the y component here. So this force is pointing somewhat in the positive y direction. This guy's also pointing in the positive y direction. And since I'm doing everything in the y direction in green, I will just rewrite right over the top of this guy and make that guy in green as well. So in the x direction, we're only considering the blue forces, a positive one and a negative one, and those two should add up to be 0. What we want to do is see if we can figure out how to describe that, but first we'll need to measure the angle. So we can measure the angle between the string and an imaginary horizontal line with a protractor, and let's say we do that, and let's say this works out to be 35 degrees. And let's say we do this over here and measure the angle between the string and an imaginary horizontal line with a protractor. And let's say that comes out to be 20. If that's true, then we know how to break up a vector into its components. And if this is m1g, this is the adjacent side here, this would be m1g cos 35. Of course, it's pointing in the negative direction. And this guy would be just regular mg times cos 20. So we would put these two expressions, these two expressions for the x forces into our x equation. Like this: mg cos 20 positive minus m1g cos 35 negative equals 0. Notice that each term has a g in it. This one does, this one does. So we can fairly divide the left and the right side of the equation by g. 0 over g is still 0, and if we divide this side by g, we cancel out a g here, and we cancel out a g here. So now we have an equation that we can solve for m. Let's do that. We'll put this negative term to the other side of the equation. We'll see what that looks like. So solving for m, dividing both sides by cos 20, we get m equals m1 cos 35 divided by cos 20. Put in a value for m1 of 0.150 kilograms. Type all that into your calculator, and you find out that the mass of the teddy bear, little m, must equal 0.1307 kilograms. Had you, instead of using the x side of the house, tried on the y, you would have three forces that were involved. You'd have this down one here, that's m2g, but negative, because it's in the negative y direction. There it is. You would have a positive mg sine 20, because that's pointing somewhat upward. And you would have a positive m1g sine 35. And again, just like before, there's a g in every single term. So we can cancel, cancel, and cancel. Everything in this equation is known except for the m, so we could move everything over to the other side of the equation, divide by sine 20, and then we could get m again, and we should get, hopefully, the exact same result. So, moving the two terms without the m to the other side of the equation, here they are, divide by the sine 20, substitute in the appropriate values for m2, which is 0.130, and m1, which is 0.15, and indeed, you get the same result. Realistically, doing this, you're probably going to get slightly different results because that depends very much on how accurately you've measured the two angles. So if your results differ by a little bit, the best thing you can do is to take those two results and average them, and that will take out whatever inaccuracies you had in your measurements of your angles. So that's how you handle a static problem. Choose a standard Cartesian coordinate system. Break up any forces that don't align with y or x into components so that they do align with y and x. Write F net equals ma for each side, and you should get exactly the same answers. Hope that made sense to you. Good luck with your lab.